Good day to you all. A study of applicability of different facing types in soil layering. I am Kumarage from NBRO. Soil layering is a technique used to enhance the stability of sloping grounds. The concept is to use the tensile capacity of rebar to enhance overall shear strength of soil. Why do we need facings? Soil layers do not stabilize exposed soil at the surface. Therefore, a facing that connects to the nails at the surface is required. Moreover, the reaction forces at the facing makes contribution to developing tensile forces along the soil nails. So the two main design elements are the system that connects the nail heads and the system that protects the surface in between nail heads. Why do we need to focus more on the facing designs? Plenty of cases have been reported around the world where soil nail slopes have failed due to the inferior facing designs. These are some of the images from Hong Kong, Malaysia, and also from Sri Lanka. Shown here are the main types of facings used in Sri Lanka. Figure A shows full face short grid facings, B shows grid beam facings, C shows bearing plates with flexible meshes, and D shows concrete pillows with flexible meshes. The images at the bottom show how these facings have fared over time and how they promote growth of vegetation. Moving on to the design of facing, the tensile force at the nail head will be discussed first. When the slip surface forms, the tensile force along the nail takes a distribution as shown in figure 4. This distribution shows how the nail head load T0 is related to the maximum nail force Tmax. Next, some of the design guides available for evaluating nail head load will be discussed. Federal Highway Administration Manual presents a formula shown in equation 1 based on the results of instrumental soil nail slopes. A parameter called the normalized nail head load is defined. And based on the results shown in figure 5, they propose to take the normalized nail head load, or FF, as 0.5 in the facing designs. A number of other studies have also justified this recommendation. Another major publication in soil nail design, Portrait 1991, also presents a different formula for obtaining nail head load. This is given in equation 2. This equation takes the vertical soil nail spacing and the maximum soil nail force Tmax as inputs. This method has been recommended in serial report for soil nail design as well for obtaining nail head loads. Table 1 summarizes the methods published in literature for nail head load. To use these methods for the calculations, two major design scenarios could be identified. To put these findings into the test, the proposed methods were applied to case history. Under landslide mitigation was one of the major landslide mitigations carried out by NBR in the recent past. The cross-section S.A.S. was considered in this study to evaluate the applicability of different facing types. The stability of this 30-meter high slope turned out to be 1.335 after the application of the proposed soil nail arrangement. To obtain the nail head load for this case history, the methods described in case 2 was used. The limit equilibrium stability analysis from slope W software was used to obtain the Tmax value, which was 145 kilonewtons. This value was input to the equation 2 to obtain the nail head loads at the facing T0, which was 116 kilonewtons. This value will be used to carry out phasing designs in the later sections. The design aspects of shotcrete phasings will be discussed here. A shotcrete phasing is essentially a reinforced concrete flat slab placed on the slope surface. Therefore, shotcrete can provide both nail head resistance as well as the protection of surface soil in between nail heads. Flexure and puncture shear are the two critical failure mechanisms. Force equilibrium of nail head load and the earth pressure behind the phasing is considered in the structural design of phasing as seen in figure 7. Both Federal Highway Administration and serial report for soil nail design present expression for structural resistance of shotcrete, considering it as a non-uniformly loaded two-way spanning continuous slab. The summary of design guides available are presented in table 2. However, none of these guides provide design steps as for the new familiar DS8110 of structural design code. As such, a new set of calculations for the structural design was presented as a part of this study. Moving back to the case history, the applicability of shotcrete phasing for the CS5 area is evaluated using the proposed modified method. Accordingly, to resist the nail head load of 116 at CS5 milling design, a thickness of 150 millimeters, 2 by 16 main rebars, and 200 by 200 head plates were required. Moreover, it was seen that the punching shear resistance is governing the structural requirement, and the punching resistance is more sensitive to the thickness around the nail head. Design aspect of grid beams will be discussed here and will be applied to the case history in later sections. Grid beams are essentially a system of reinforced concrete beams constructed across the slope surface connecting the nail heads. Although shotcrete facings transfer load throughout the whole soap surface, grid beams limits the load transfer to the beam width. Therefore, steel meshes are typically installed on top of the grid beam needs to account for the local instabilities. Flexure or shear resulting from the nail head loads are the critical failure mechanism concerned in the structural design. Hong Kong Institute of Engineers report for designing village structures is adopted in the study for grid beam designs. There, the beam is treated as a simply supported beam with earth pressures as a UDL. However, the structural design is based on the Hong Kong Code of Practice. As such, in the study, a modified procedure for calculation for structural design of grid beams were presented based on BS810. Moving back to the case history, the proposed method was utilized in determining structural requirement of a grid beam at CS5 area. Accordingly, the beam size of 250 by 250 by 12 full main rebar and R10 shearings at 150 meters were required for the grid beam. Design elements of concrete pillows will be discussed next. Unlike the grid beams and shotcrete, pillows transfer loads into a smaller area of the slope. Therefore, the capacity of the pillow facing is governed by the bearing capacity of the slope surface. The load transfer of pillows could be analogized to a pad footing of a building. The summary of the design methods available in literature are presented in Table 5. Almost all these guides refer to the lower bound method, which was initially presented in the Highway Agents Design Manual of England. The calculation carried out using this method for the case history revealed that a pillow size requirement of 800 by 800 reduces the obtained nailhead length. This size requirement makes the pillow option less appealing with a relatively larger size. Moving on to the design of flexible facings, the flexible mesh facings must resist the force from local instabilities in between grids and pillows and transfer it into the nail head place. However, in the case where the bearing plate alone is used as a nail head without pillows or grid beams, the mesh must resist both the nail head load as well as the local instabilities. This is because the smaller footprint of the plate does not generate adequate bearing resistance against the slope. Major publications available for flexible designs are Sigma report for soil nail design and the work done by Roger and others. Sigma presents a two-part wedge failure mechanism method as well as a single wedge mechanism. Ruger and others also present more advanced two-body failure mechanism and one-body mechanism compared to the Syria as seen in Figure 12. All four discussed methods were put into the Haggadah case history to obtain force induced by local instabilities where grid beam facings have been constructed. The poor water pressure conditions used, which is an extreme scenario, seems to have caused Syria report approach to produce larger force of 40 kN. However, this will be conservatively used for selecting the appropriate mesh for this application. Moving on to the design of mesh to be used with pillow nail heads. Because of the zigzag nailing pattern used in pillow systems, the height of the two-part wedge model H becomes twice of the vertical nail spacing. Therefore, the force on the mesh from local instabilities will be higher when the pillow facings are used. Accordingly, the out-of-balance force obtained for the same case was 95 kN in the pillows as opposed to the 40 kN obtained in the grid beams. As such, a mesh that produces higher plunging shear resistance will be necessary for these applications if pillows are used. Moving on to the bearing plate with flexible mesh facings, in this case, the metallic mesh itself must be designed to withstand the nail-head load due to the smaller footprint of the bearing plate. In the case of our case history, the mesh must have a punching shear resistance greater than the nail-head load, 116 kN. A higher capacity mesh requirement makes the bearing plate facing method a more expensive option compared to the other facings. The cost of different facing options discussed were assessed. Comparison in Table 8 was carried out based on the current market prices of slope mitigation projects in Sri Lanka. It could be seen that full-face shotcrete facing is considerably expensive compared to the pillow and grid beam methods. The metal bearing plate method, which utilizes high tensile wire meshes, turned out to be the most expensive method due to the higher cost of mesh. I will finish with my conclusion. The grid beam and shotcrete facing offer the most freedom to achieve a higher nail-head resistance value. Full-face shotcrete is superior to grid beam in terms of the ability to resist both nail-head loads as well as local instabilities, but the ability to introduce vegetation in between beams would make them aesthetically pleasing. The cost of shotcrete is relatively high and ability to dissipate water pressure is low compared to the grid beam and pillow options. Isolated nail-head system with planting soiling or hydroseeding would blend with the natural landscape. However, the out-of-balance force from the local instabilities is high and the tensile metallic product would be required. But the concrete pillows would still provide a viable economical option. The larger size of the pillars would impose construction difficulties. If metal bearing plates are used, it would demand the use of metallic mesh with even greater tensile strength, and it would make it uneconomical. For residual soil formation in Sri Lanka, the beams with metallic mesh could be preferred as an economical structurally superior solution that is aesthetically pleasing. However, on the slopes, where the rolling joints and collapsibility is present, keeping the sites of the excavation stable would be challenging in the case of pit beams.